Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept regarding the force exerted by the jet on a stationary inclined plate. So in our last lecture, we have discussed similar kind of things, but in that time we have taken vertical plate. Now we have considered the plate is inclined condition. So what is the force exerted by the jet on a stationary inclined plate? We need to find out. So here I have taken, suppose this is the pipe is there. This is the actually pipe is there. Through this pipe, the water is flowing or the liquid is flowing through this pipe, and this is the fluid which is flowing through this pipe. Okay, and near to this, a nozzle is connected to this one. This is the nozzle part, and the jet of water. So the jet of water, the jet of liquid, which is coming out from the nozzle or from the this pipe to nozzle to here, we can see. So the jet of water which is coming out from this is with a velocity of v, and that is going to strike over a plate, a flat plate, but the plate is here inclined condition. Okay, previously we have seen the plate was in the vertical condition. Now we have taken this plate is in inclined condition. And second thing is, previously we have taken the plate was in vertical condition. Now you can see we have taken this plate with an inclined condition with an angle of theta. So you can see this is the velocity of the jet, or this is the jet movement, and this plate is makes an angle of theta to this one. And third thing is the plate is stationary. That means the plate is not in the moving condition, it is in the fixed condition. Stationary is nothing but this is a fixed one. Okay, so three things are there. First, we need to consider the jet of the fluid. Second is the plate should be inclined, and third one is it should be stationary, or it is in fixed condition. So these are the terminology are used in this concept. So we need to find out what is the force exerted by the jet. Now same thing, I'll just tool this diagram a little bit here. Suppose this is the jet movement is there, the jet of fluid which is moving in the x direction, suppose, and this is the velocity v, and the plate which is fixed here, let consider the plate in some different color, and here I'll consider this plate like, suppose this is the plate is there which is placed with an angle of theta here, you can see. So this angle is theta here. Obviously the opposite to this one also will be theta angle here. So this is the plate, okay, and which is fixed, you can see, which is fixed, and this is the velocity. Okay, now the next thing is we need to consider what are the terminology we can use here. So we have seen this water is coming out from the nozzle of this pipe, and it is striking over a inclined flat plate. And here first one, as I told you, that velocity. So velocity, we can consider this is capital V, which is velocity of jet with in the direction of x, in the x direction we can consider. Okay, you can see this is the x direction, so this is suppose xx. Okay, and obviously vertical to this one will be if I draw this one like this one, so this will be our y direction. Okay, and similarly the next one is this is velocity v, and next one is theta. So theta is the angle between the, we can see this is the jet. Okay, this is the jet, we can see here, already mentioned there, and this is the flat plate. So theta is the angle between jet of water and the plate. Okay, and next one is area we need to consider here. As you can see here, this is the total jet which is coming out from here, so that one you can consider as small d diameter. So this is diameter of the jet, so this is diameter of jet, and from here we can calculate the area, small a. This is area of the jet, so this one also we can calculate with the help of this formula, like pi by 4 and d square. So this is the area. And next one, we can calculate the mass of water, the mass of water per second. So mass of water, which is striking, mass of water per second striking the plate. This is striking the plate. So this is nothing but the mass flow rate we need to consider. So this one actually we have already knows previously this one, like last class if you see I have already derived this one. This is actually rho A V. So this is nothing but I can simplify here. Okay, so this is mass of water per second. So this is nothing but mass per second. So second is nothing but I can write mass per time, and this mass part I can write in terms of, we know that rho equal to density equal to mass by volume. So here I can write mass equal to rho into volume. So again same thing I'll write here, rho into volume per time, rho into volume per time. So this volume per time is nothing but, we know that discharge equal to, or discharge are nothing but flow rate. So discharge equal to, we know that this is unit is meter cube per second, and this is nothing but the volume of water which is coming out from with respect to time. So this one we can write discharge, and discharge also we can write in terms of area into what? Area into velocity. So same thing we have done here, rho into Q, and this one we can again we can write this is rho A V. Okay, so the mass of water per second striking the plate is nothing but rho A V. So this is one part. Okay, this is one of the part. And now what we need to calculate? We need to calculate the force exerted by the jet. Now see, the force exerted by the jet on the stationary inclined plate. So this is the inclined plate is there. Now we need to find out, see here the jet of water is moving with the in this direction. So obviously the force which will be exerted by the jet on the plate also will be Fx. So you can write this is suppose Fx, and this is Fy. Okay, and now though the plate is in inclined condition, so the force also will act on this as a incline. So first of all we'll find out what is the, always keep in mind that when the force will be impacted on any kind of object or any line, so we need to consider the normal force which is impacting on the plate. So first of all we'll find out what is the normal force which is acting to this plate. Suppose this is the normal force which is acting to the plate here, and this one we can give a Fn, and the normal force which is acting on the plate, okay, let derive up to here. Okay, this is the normal force which is acting on the plate, and that to be obviously it will be perpendicular. So we can write this is perpendicular theta. Okay, now here you can see this part is theta is there, and this is also theta. Now the remaining part will be what? Remaining part will be this is 90 minus theta. We know that. So because it is perpendicular, you can see this is the perpendicular what I have taken to this plate. So here if I consider that this remaining part is nothing but 90 minus theta, and this is the force which is acting on the plate, inclined to the plate. So here what I can first identify, see why I'm focusing on the Fn, because here I can see the force exerted by the jet on the plate with an inclination. So we need to consider the force should be normal to this one, to the plate. Then from that we can identify some components. So the force which you have normal force what we have taken, that we need to resolve in two conditions. One is x direction component, another one is y direction component. So this one previously you may have heard these things, that a component of force in resolved in two directions or two ways. So that that will be written Fx equal to, or here Fn equal to we can write. Now see, this is the theta value is here, that is 90 minus theta. Now here if I resolve, now let me write here one more point here also I can write Fn. So Fn is nothing but the normal force the normal force, which is developed by the jet, the normal force which is developed by the jet. Okay, so the normal force let resolve in the x and y direction. So here also let fy. So if I resolve this one in the x direction, so I can write this is f x direction, let write it. So that is nothing but the force which is acting this one with respect to this angle. So this angle will be resolved in the x direction, that will be written, this is nothing but cos theta. So cos, this is 90 minus theta. So cos 90 minus theta is nothing but, we can write this is fn sin theta. Okay, and similarly, what about the fy, the force in the y direction? So let's see the force in the y direction. So this normal force, again we need to consider in this y direction. So again we can write this is fn, and when it is perpendicular we need to consider this is sin theta. So that is nothing but sin 90 minus theta, and this one we can write this is fn, this is cos theta. Okay, so this one I hope you understand. This is the mass flow rate, rho av, and this is the force acting on these directions. Okay, now we need to calculate, now we need to calculate the fn value. So this fn value, as I told you that this one we need to calculate. So I'll say one more thing here. We need to calculate the fn, the force. Okay, so the force, we know that as per the Newton's second law of motion, we know that force equal to F equal to m into a, so mass into acceleration. So this one again we can write, we know that this is can be written that mass into acceleration equal to, we know that change in velocity with respect to change in time. Okay, so this is nothing but the rate of change of momentum, also it can be written like this. And again we can write this is mass per time. So let's write mass per time, and this is change in velocity, this is nothing but v1 minus v2. So this part again, mass per time is nothing but, we can write this m dot, okay, m dot into v1 minus v2. So this one already we have calculated, the mass of water per second which is striking the plate, that is m dot. So that one already we have calculated, rho av. Next we need to find out what about the velocity v1 and what about the velocity v2. Okay, so this is about normal, just I'm talking about the force. Now we need to identify what to calculate this fx and fy, because the force exerted by the jet on the stationary inclined plate. So the force, this force we need to identify, okay, fx. So to calculate the fx, we need to identify fn. So, and here I'm calculating the fn value. So this is on place of f, I can write fn, the normal force, this one, the normal force, this one. So here also we need to consider the velocity of fluid normal directions. The velocity component also we need to consider in this normal direction which is striking to the plate. So this is initial velocity and this is final velocity. Now the final velocity is nothing but, now see, when the velocity is striking this plate, here initial velocity we can consider this is v, okay, and after striking here we can see, after striking the water on this plate, at this point the velocity is going to be 0, okay, because it is a fixed plate and the plate is not moving any direct in x direction, there is no movement is there in the plate. So after striking here at this point, the velocity is 0, because you can see the fluid velocity which is initially the same is velocity is leaving with an angle of theta, go to outside. Okay, that's why at this point we'll get a value of 0, that is v2. But what about the v1? So v1 we cannot consider in this v, because we are calculating the normal force. So for normal force also we need to calculate what about this velocity, at this velocity, at this direction, what is the velocity value v. So to calculate this velocity value v, we need to do another one thing. Now suppose this is the plate is there what we have taken. Okay, let this one draw a perpendicular from here, from this inclined line to this jet direction, this one. Okay, So this angle, I'll do it here again. So let's suppose this is the fluid movement, V is there, you can see, and this is the origin point, O point, suppose this is O point, and this is the plate is there, this is the plate, okay, and this is the normal direction, this one you can see. Why I have taken this normal direction, this this line, because this line also and this force of this one, both are parallel. So if I able to calculate the velocity at this point, the same velocity I can consider in this component also. So for this, what I'll do, suppose this is O and this is P and this is Q, and here I can consider this is my, already I have taken, this is the theta value, you can see here, this is the theta I have taken, and this is our normal perpendicular, this one. So in this triangle, you can see this is our base point, this is our base, and similarly this is our perpendicular height, this is our perpendicular height is there, and this is our hypotenuse, this is our hypotenuse is there, and this is perpendicular is there, this is P, and this is B we can say, and this is H we can consider. Okay, now what I need to, and this is the velocity V in this direction, correct. Now here, as per this concept, what we can write, as per this concept we can write, let me write in this, we know that sine theta equal to, we can write sine theta equal to this perpendicular by this hypotenuse H. And similarly, if I calculate the cos theta, here I need to consider the base of the triangle with respect to the hypotenuse. So hypotenuse always will be there in this. And what actually I need to calculate? I need to calculate this value, this PQ value. Okay, this perpendicular height value. So P is where in this equation, you can see P is here. So P equal to, we can write, this is H into sine theta. H into sine theta. So H is nothing but what? This is our H. So H value means OQ. So OQ plus, I can write here, what is the value here? P equal to, I can write this is V sine theta. V sine theta. So V sine theta is which one? This one I have taken, V sine theta, PQ value, correct. So PQ equal to this same velocity component in this direction. So the way V sine theta, I can write for this component also. So here what I can write, Fn equal to, yeah, this is mass flow rate, that one we can write rho AV, and this is V sine theta, not bracket, this one, yeah, this one minus 0, final velocity, and finally you can write this is rho AV square sine theta. Okay, this one we can give equation 2, and this one we can give equation. Okay, now what we need to do, we need to find out the force which is resolved in the two directions, the normal force which is resolved in the two directions, like x direction and y direction, and that force we need to find out. So again, immediately we write this one, like the value of fx. So this one, the value of fx, what we got here, the component of fn, in the direction of flow, that is fx is nothing but we got already, this is Fn, this is sine theta, Fn sine theta. I hope you are getting this point. So Fn already we have calculated here, just now we have calculated, that is nothing but rho AV square sine theta. So here sine theta again into sine theta, so you can get it here, this is rho AV square sine square theta. This is equation number 3. Okay, similarly we need to calculate the force in the y direction. So this is F in the y direction is nothing but the component of Fn, in the y direction or perpendicular to the flow. So here also we can write, this is already we got here this equation, Fn cos theta. So this one also let's write Fn cos theta. So same thing I'll just write here, rho AV square, and this is sine theta into cos theta. Okay, so as usual just I'll write the same thing, answer here, this is the final answer, rho AV square sine theta into cos theta. If you want to resolve in more, also you can resolve by multiplying 2 and dividing 2, then we can get it like sine 2 theta. Okay, so this is our final answer for this. So force exerted by the jet on the stationary inclined plate. So here you can see this is stationary condition or fixed. The plate is fixed and the plate is inclined. Okay, and these two diagrams you just keep in mind. So this one what I have drawn for this velocity component, and this one was drawn for the velocity like a force, the normal force which is acting on the fluid flow. So I hope you understand this, and still if you're having any kind of query doubt regarding this, you can give a comment on the comment box.